Ever wonder how those architects design these like massive skyscrapers, or even just like how we even measure the height of something we can't reach, like a mountain?
It's pretty amazing how one, like, fundamental shape can unlock so much about, well, the world around us, really.
Right. Like for real. I was thinking about this earlier, and imagine a photo
Mm-hmm.
you want to blow up, like to poster size,
Yeah.
or even shrink down to fit, in a locket or something.
Yeah.
You can change how big or small the picture is, but it's still the same picture.
Right. Right.
That, my friend, is similarity, like in action.
Exactly. Yeah, we get that, right? Like instinctively, two things can be, similar without being like identical. It's kind of like siblings.
Oh, okay.
Similar, yeah.
Yeah.
Same family resemblance, but maybe not the same like height,
Yeah.
eye color.
Okay.
Same thing in geometry. We call figures that have that same shape, but not necessarily the same size. Similar figures.
Okay. That makes sense. But how is that different than congruency? Because those two words always kind of trip me up in school.
Yeah, it's a common point of confusion for sure. But think of congruency as identical twins. So same shape, same size, basically mirror images of each other.
Okay.
Similarity, bit more flexible. So all congruent figures are similar, but not all similar figures are congruent.
Got it. So are you saying that like a tiny equilateral triangle is similar to a giant one, even if they're like miles apart in size?
Exactly. And our source material kind of reminds us all circles are similar to each other. All squares are similar to each other.
Right.
Again, it's that same, at their core, they share that same fundamental shape.
Okay. Yeah. That makes sense.
Yep.
But you can't tell me that like a square and a circle are similar. They're totally different.
You're spot on. But that's the beauty of geometry, right? It gives us a way to like define and prove these relationships that we kind of understand already,
Okay.
For polygons to be officially, and I say officially, classified as similar, they need to meet two specific conditions.
All right. Let's hear them. What makes one shape officially similar to another?
Okay, so the first condition is that their corresponding angles must be equal.
Okay.
Imagine shining a light and you're creating like a shadow of a shape.
Okay. Yeah.
The angles in the shadow are the exact same as the angles in the original shape, even though the size is different.
Oh, that's a good visual. What's the second condition?
The second condition is that their corresponding sides must be proportional, meaning they all change by the same ratio or like scale factor.
Okay.
Think of our photo example. You double the width of the photo to keep it, you have to also double the height to keep the picture from looking all distorted.
So it's all about keeping it in proportion.
Exactly.
And just to be clear, when we say corresponding angles or sides, we mean like the ones that occupy the same like relative position in the figures.
Precisely. It's all about comparing apples to apples. Now, let's apply this idea of similarity to a shape we encounter literally everywhere and honestly considered like a building block of geometry. The triangle.
Triangles.
Yeah.
Ooh, triangles. They always felt so like fundamental, but I could never put my finger on like why. What makes them so special in the world of geometry?
Triangles are so fascinating because they're incredibly stable and versatile. Like, understand triangles, and a whole world of geometric concepts starts to make sense. Even thousands of years ago, mathematicians recognized this. Our source mentions Thales and his basic proportionality theorem, a groundbreaking discovery for its time.
That sounds kind of intimidating, but I have a feeling you're going to break it down in a way that even I can understand.
Absolutely. So in simple terms, the basic proportionality theorem, it says that if you draw a line parallel to one side of a triangle, it divides the other two sides proportionally. The source explains it with a really clear activity involving like points on the sides of a triangle.
So it's not just some abstract theory. There's like a hands-on element to it. I like that.
And the beauty of it is that it has real-world applications. Think about how surveyors measure distances or calculate the height of a mountain. They can't exactly use like a tape measure for that, right?
That's true. I'd hate to be the one holding the tape measure at the top of Mount Everest.
Yeah.
So how do they do that?
They use similar triangles.
Oh.
By measuring angles and like accessible distances, they can create similar triangles and use those proportional relationships between their sides to calculate those unknown measurements.
Wow. That's incredible. So you don't have to climb every mountain or measure every distance directly. Similar triangles give you like a shortcut.
Exactly.
And speaking of shortcuts, don't similar triangles have like special properties that help us figure out quickly if they are similar, just like congruent triangles do? I vaguely remember this from school.
Yes, you're right. There are shortcuts. We call those our similarity criteria.
Okay.
And just like you said, they give us a way to determine if triangles are similar without having to prove every single angle and side are congruent. And in math, as in life, efficiency is key.
Okay, you said efficiency is key.
Yeah.
Like the sound of that. So tell me more about these shortcuts, these criteria that let us just skip right to proving that triangles are similar.
All right, so we've got three main ones,
Okay.
which is like with congruency. And remember how we were talking about how you need corresponding angles to be equal and corresponding sides to be proportional for triangles to be considered similar?
Right.
These criteria let us prove similarity with less information.
Okay, less work. I love it. What's the first shortcut?
First shortcut, it's called angle, 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 or AAA.
Okay.
This one's all about those matching angles.
Okay.
If we can show that all three corresponding angles in two triangles are equal, then boom, those triangles are similar. We don't even have to touch the sides.
Yeah.
Because if the angles are equal, the sides have to be proportional.
Wow. So we could just skip measuring all those sides.
Think
That's
so.
super efficient. Okay. What about the next one? What's our next shortcut?
Next one, we've got side, 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 or SSS.
Okay.
And this one flips the script a little bit.
Okay.
So if we know that all three pairs of corresponding sides in two triangles are proportional, then those triangles have got to be similar.
Got it.
So it's like those side ratios just lock those angles into place.
And it's like the sides are like dictating the shape of the triangle.
Yes,
It's so cool.
It's pretty neat.
Okay. Last shortcut. What have we got?
Our last shortcut, we call it side angle side, or SAS.
Okay.
This one's kind of a combo deal.
Okay.
So if we have two triangles where two pairs of corresponding sides are proportional, AD, the included angle, that's the angle between those sides, is equal in both triangles, then we've hit the jackpot. They're similar.
So it's like we need that one matching angle, but it has to be like nestled between those proportional sides.
Exactly.
It's like the missing piece of the puzzle.
Yeah.
Okay, this is really cool. Like these criteria are super cool. They give us a really fast track to proving that triangles are similar. But like, why does it even matter? What can we actually do with this information?
Well, that's the best part. Knowing that triangles are similar unlocks, honestly, like a toolkit of problem-solving techniques.
Okay.
One of the most elegant examples, in my opinion, is that we can actually use similar triangles to prove the Pythagorean theorem.
Wait, hold on. Are we talking about the Pythagorean theorem? The one that everybody remembers from high school, even if they like swore off math?
That's the one.
Okay.
The one and only. Yeah, you probably remember the formula. A plus B or C fly.
Yes.
Tells us about the relationship between the sides of a right triangle.
Right.
But what a lot of people don't realize is that this really famous theorem, often learned by like rote memorization, can actually be proven through the elegance of similar triangles.
Okay. I am very intrigued. But before we dive into that, can we just, I don't know if everyone remembers, what makes a triangle a right triangle?
Of course. So right triangle is simply a triangle where one of the angles is a right angle, meaning it measures 90 degrees, like the corner of a square.
Right. Right angle. Got it.
Exactly.
Okay. So back to this elegant proof that you were talking about. Give it to me. Don't go full on textbook mode on me or anything.
Okay. No textbook mode, I promise. The key here, it lies in what happens when you drop what we call a perpendicular line.
Okay.
From the right angle of a right triangle down to the hypotenuse, which is the side opposite the right angle.
Okay.
What this does is it creates two smaller triangles within the larger right triangle.
Okay, so I'm picturing it. We've divided our one big triangle into two smaller ones. Now what?
Here's where the magic happens.
Well,
these two smaller triangles are similar to each other. A and D similar to the original larger triangle.
wait a minute. How do we know that?
Well, it all goes back to those angles. Remember, we've got our AAA similarity on our side.
Right.
The right angle is shared by all three triangles.
Okay.
Then each smaller triangle shares one of its other angles with the larger triangle.
Right.
So since we already have two matching angles in each pair of triangles, that third angle, it's guaranteed to match as well. Because remember, the angles in any triangle always have to add up to 180 degrees.
Oh, that's right. I forgot about that fundamental rule.
Yes.
Okay, so we've got all these similar triangles just hanging out inside our right triangle.
Yeah, right. Exactly.
What's the next step in this elegant proof of ours?
Well, because we know those triangles are similar, we can use that fact that corresponding sides of similar triangles are proportional.
Right.
So we can set up these ratios based on the sides of those triangles. And what we end up showing is that the areas of the squares that are built on the legs of the right triangle, so that's A plus B,
Mm-hmm.
will always add up to the area of the square that's built on the hypotenuse, which is C.
So similar triangles are like the secret ingredient to proving one of the most famous theorems in geometry.
Oh, no, it's so cool.
That's incredible how it's all like connected. It
Yeah.
makes those like seemingly random formulas you learn in school. It's like, oh, it makes sense.
Right, it just clicks.
Yeah.
And that interconnectedness is one of the really, really beautiful things about math in general. But similar triangles, they've got even more to offer.
Okay.
Our source also talks about theorem 6.6,
Okay.
which goes into the relationship between the areas of similar triangles.
Okay. I'm ready for theorem 6.6. What's it all about?
Okay. So in simple terms, this theorem, what it states is that if you have two similar triangles, the ratio of their areas is equal to, are you ready for this?
Yes.
The square of the ratio of their corresponding sides.
Okay.
Yeah.
I think I get it, but can you give me an example to make it click a little bit more?
Of course,
Yeah.
yeah. Imagine you're baking a cake
Okay.
and you want to, let's say, double the recipe. You double the measurements of all the ingredients. Essentially, you're creating similar cakes, right?
Mm.
One smaller, one larger.
Yeah.
But here's the catch. Doubling those linear measurements doesn't just double the area of the cake, it quadruples it.
Because you're increasing the length and the width, so the area is going to get like way bigger faster.
Exactly. And that's what this theorem is getting at, you know? It's not just this linear relationship.
Right.
We have to square that scaling factor. You triple the sides of a triangle. The area isn't 3 times larger, it's 9 times larger.
Wow. That's crazy. And I bet you that applies to all kinds of shapes, not just triangles.
Absolutely.
Yeah.
Yeah, it's got huge implications for, you know, everything from designing buildings to understanding how, like, forces act on objects of different sizes.
Right. Like if you tried to make, I don't know, like a human-sized Lego out of the same materials, it would never support the weight.
Exactly. The strength wouldn't scale the same way.
So it's like not just about these abstract shapes on a page. This is like, you know, real-world stuff. Architects, engineers, bakers even.
Exactly. And what's really fascinating is I think we've really only kind of scratched the surface here with similar triangles, you know. Our source material, it even hints at like even more relationships and applications kind of hidden in some of the optional exercises.
Ooh, you're like that friend who mentions a secret menu at a restaurant. Now I gotta know. What kind of secrets are we talking about?
Well, I don't want to, you know, spoil the fun for everybody. Sometimes like those aha moments when you figure something out on your own, those are the best.
Right.
But let's just say there are some really elegant proofs and kind of surprising connections waiting to be explored. I mean, who knew triangles could be so interesting?
You've definitely like piqued my curiosity. I might have to dust off the old geometry textbook later.
Yeah.
But, you know, before we get too carried away with like all this secret triangle stuff, you've got me thinking, we've been, you know, looking at all this through a mathematical lens, but this whole idea of similarity, it's got to reach way beyond textbooks and classrooms. Right?
Oh, absolutely. Yeah. Once you start like noticing similarity, you see it everywhere. Think about, you know, architecture, the way that like buildings use these repeating geometric patterns and like scaled elements, you know, to create a sense of grandeur or harmony even.
Oh, yeah.
Or even look at nature. You see it in the branching patterns of trees, the spiral of a seashell, even like the veins of a leaf. They all exhibit these, you know, principles of similarity.
Yeah, right. It is everywhere. Once you like start to look for it,
Yeah.
can't unsee it.
Exactly.
Well, this has been awesome. I feel like this deep dive has given me a whole new perspective on the world around me. So thank you for that.
Oh, of course. Happy to do it.
Who knew something as seemingly simple as similar triangles could, I don't know, unlock so much understanding about, you know, architecture, nature, even baking?
It really is amazing. You know, it's a testament to, well, first, the power of geometry, but also like the elegance of mathematical relationships in general, right?
Yeah.
These concepts, they give us a framework for understanding the patterns and proportions that, you know, honestly shape the universe.
Well said. And on that note, we're going to wrap up this deep dive into the fascinating world of similar triangles. We hope you've learned something new, and maybe you even have a new perspective on the hidden connections that are all around us. Until next time, keep exploring, keep questioning, and most importantly, keep those aha moments coming.